Hello everyone, this is Yijun Li from Adobe Research, and I'm honored to present our paper about controllable and progressive image extrapolation. This is a joint work with Lu Jiang and Mingxuan Yang. The goal of image extrapolation is to expand the narrow field of view of a given image. Its potential applications include panorama creation, auto-resizing, and so on. Early methods are mainly based on nearest neighbor search and copy, and they are only able to handle homogeneous regions and hard to synthesize semantically new pixels. Following works apply deep learning to treat this task as a conditional image generation problem. However, they have no controls over the extrapolation process and only output a determined result. In this work, we focus on two aspects. First, we targeted on extrapolating object images with semantically new pixels. Second, we aim at generating diverse extrapolating results with the text as control signals. There are two inputs to our model. One is a target image patch, and the other one is a text signal, which is representing a scene graph containing object parts to be extrapolated and their spatial relationships. The output is extrapolated results. Inspired by human drawing techniques, we propose a progressive generating model of three stages: generating a coarse bounding box layout, refining it to a finer segmentation layout, and mapping the layout to a realistic output. The stage 1 takes a scene graph as input and outputs a bounding box spatial layout map. It consists of a GCN and a regression network, which are regularized by a bounding box loss that minimizes the coordinates difference between the predict box and the ground truth bounding box. Given a graph with embeddings initialized at each node and edge, the GCN computes new embeddings for each node and edge through propagating information along edges of the graph. Then, the encoded object embeddings are fed into the regression network to predict the bounding box coordinates. Stage 2 is transforming the coarse bounding box layout into a segmentation layout conditioned on an image patch, and the network is learned with a pixel-wise multi-class cross-entropy loss. This stage not only generates the segmentation layout for the unknown regions, but also needs to align the unknown and the known regions. After obtaining the segmentation layout, stage 3 operates as a label-to-image mapping model in a way similar to image-to-image translation. We employ the perceptual loss and adversarial loss for network training. We conduct experiments to validate the effectiveness of our model on two types of object images of great interest: the face and the human body. During the training process, for each input image, we crop image patches of random size at random positions and train the network model to recover the original image. Here are the visual comparisons with previous method and baselines. Overall, our model generates sharper and more realistic results. We show the layout and the final result of our model here. This is the quantitative evaluation using the exception score and FAD score to check how close the results are to the real image distribution. Still, the proposed method achieves best results across both datasets. We also conduct user studies to analyze human perceptual preference towards different methods. We collect 300 votes from 20 participants. The proposed method received the most votes from users, which is significantly higher than others. A unique property of our method is that we can control image extrapolation with different text inputs. Below, we show different extrapolated results from the same image patch, but with different text inputs. The results show that our model follows the control signals specified in the scene graph very well. To conclude, in this work, we propose a progressive extrapolation pipeline by generating the layout as an intermediate step, and we can control the extrapolation process with text signals. Please check our paper for more details. Thank you.